Hi, my name is Ariella Mansfield, and today we're going to discuss graph search approaches to path planning for robotics. The basic motion planning problem deals with developing techniques that allow a robot to automatically decide how to move from one configuration to another. We are looking for a path through the configuration space that takes our robot from an initial configuration, denoted by QI, to a goal configuration, QG, while avoiding the obstacles marked here in teal. Path planning may sound simple, but it's among the most difficult problems in computer science. We want to find a complete algorithm, meaning that it finds a solution wherever one exists, and signals failure in finite time when no solution exists. Planning algorithms may be used to find paths in cluttered environments, such as the one seen on the left, where the robot has to navigate through all the debris and around the pillars, or to find paths that are obstacle in some sense, such as the example on the right, where we want to find the shortest path between two cities. In previous lessons, we discussed the forward kinematics of a robot. This allows you to determine the position and orientation of the end effector in the workspace given the joint variables. Since we assume a manipulator robot is composed of rigid links, the joint variables completely specify the location of every point of the robot and gives us the configuration of the robot. The set of all possible configurations is called the configuration space. Our planning problem will be defined in the configuration space. We denote by script W the Cartesian workspace in which the robot moves. There may be numerous obstacles in the workspace. We denote these by O with an associated numbered subscript. A collision occurs when the robot comes in contact with an obstacle in the workspace. We define a function A that takes a configuration from the configuration space and gives the corresponding area of the workspace. This allows us to denote by A of Q the subset of the workspace that is occupied by the robot when it has configuration Q. The set of configurations for which the robot collides with an obstacle is referred to as the configuration space obstacle. In the last lecture, we discussed some methods for determining the relationship between the robot's configuration and whether it intersects any of the obstacles in the workspace. We will usually try to do all of our planning in the free configuration space, which is the set of all collision-free configurations. That way, our robot can follow a path without colliding with any obstacles. Let's start with a simple example. Here we have a point robot on a plane. So its configuration is fully defined by the workspace, R2. There are two obstacles, O1 and O2, and the area in the workspace outside those obstacles is the free configuration space. We note the start location of the robot and the desired goal configuration. The simplest path between these two configurations is simply a straight line. However, it is clear that in this case, following a straight line would cause a collision. Instead, the robot's path must go around the obstacle to reach the goal. The question that the planning problem must answer is, how do we find this curve? What is the best curve to follow? To make the problem tractable, we formulate our problem as a graph search problem. The first step we take is to discretize our space. In this case, the way we're discretizing it is by overlaying the configuration space with a uniform end-by-end grid. We remove any grid cells that contain obstacles and find start and end cells. The first algorithm we'll see is the wildfire algorithm. This algorithm gets its name from its behavior. It spreads like a fire from a given location, moving throughout the free configuration space. We start by marking our start configuration with a value of 0. Then we find all of the nodes that are one step away from the start and mark them with a 1. Then all of the nodes that are one step away from those, meaning 2 steps away, and mark them with a 2. Note that we skip all of the obstacle cells. And our fire continues to spread, and we get 3 steps away, and we continue spreading out until we have searched all of the cells in the configuration space. And we're going to update each cell with how many steps it is away from the start. The next algorithm we will look at is the BFS algorithm. We start out, once again, by assigning a value of 0 to the start node. We maintain a queue of nodes to expand, starting with the neighbors of the start node, marked in light blue. We mark their values as 1 step away from the start. Now, moving to the next cell in the queue, we look at its neighbors, and we give them a value of I plus 1 steps from the start. Now that we've expanded this node, we remove it from the queue and move on to the next cell in the queue. We add its neighbors and update their values, and we continue iterating through all of the different nodes in the queue, updating the neighbors as we go along. And now we have arrived at a node whose neighbor is our goal. By backtracking, we can now find a path from the start to the goal. In the worst case, this algorithm will search through all of the cells of the graph. This worst case complexity is usually described in computer science using big O notation. And in this case, it is dependent on the number of cells and on the edges between them. The algorithms we explored so far will give us an optimal path when the cost to come to each cell in the grid is uniform. But we can ask, what about situations where the cost is different depending on our location within the graph? In this case, we can use a graph representation of the configuration space, where each cell from our discretized configuration space is represented by a vertex. Neighboring vertices are connected by edges. We can assign costs that don't need to be uniform, and they represent the values we might want to minimize when we're talking about optimality, such as distance, time, or energy spent to go between configurations. Wherever there are obstacles, we must remove all the surrounding edges. This will prevent our algorithm from choosing paths that collide with obstacles. A graph is defined by its vertices and edges. An edge joins two vertices and is represented by the set of vertices it connects. Edges can be directed or undirected. For a directed graph, edges are represented by an ordered pair, and for an undirected graph, by an unordered pair. The costs associated with traversing between nodes in the graph are represented by edge weights. A well-known algorithm for finding optimal paths in a graph with positive edge weights is Dijkstra's algorithm. We start by marking the cost to come to the start node as 0. We add all the neighbors of the start node to our boundary. We update the cost to come to each of these nodes based on the edge weights. We continue this algorithm while we still have nodes that we want to expand in our boundary. And we choose, marking with the blue frame, our next node to expand based on the node that has the minimum cost that's in our boundary. We add all the new neighbors to the boundary and update its costs based on edge weights. Now that we've finished expanding this node, we remove it from the boundary, and once again, we need to find the next node to expand. We're going to wait until we have a node that is a neighbor of the goal, because that is what we ultimately want, a path from the start to the goal. And now we've chosen the next node within our boundary that has lowest cost. We add its neighbors, update their costs. Go to the next node, find its neighbors, update their costs, and so on. And now we finally reach the case where the neighbor of our current node is the goal. So we're going to store that path. But are we done? Have we found the best path to the goal? Not necessarily. We see that there's still other nodes that have a cost that's lower than the cost of our goal. So we're going to continue expanding them until we reach a situation that we have now, where the lowest cost of all the lowest cost of the cells in our boundary is the cost of the goal. And now we know that the last path that we stored, that is the optimal path to the goal. This algorithm could potentially search through all the cells. If one takes into account also the operation of finding the minimum node to expand within the boundary, then using big O notation, the computation cost of this algorithm in the worst case would be O of V log V plus the number of edges. A question arises, can we do better than Dijkstra's algorithm? Is there any other information left on the table that we can utilize to speed up this search? We can use extra information to speed up our search. If we know where the goal is, we can add a heuristic that estimates the distance of the path to the goal. Then we can add the cost to come to the node with the heuristic of the estimated cost to go from the current node to the goal. This becomes the new function by which we prioritize our expansion of nodes. The algorithm we saw before, Dijkstra's algorithm, can actually be viewed as a special case of A*, where our heuristic is just 0. A common heuristic to choose is the Euclidean distance to the goal. Let's show the previous expansion that we did before, where we include also Euclidean distance as our heuristic, shown here in parentheses. We're going to start out by expanding the node with the lowest value of both the cost to come and the cost to go, which over here is going to be 1 plus 2.8, 3.8. Once we've expanded that, we see that this directs our search more clearly towards the goal because our next node to expand is going to be the node currently in blue, which has a combined value of 4.2. And then we continue expanding out other nodes, and much more quickly we reach our goal, which we've done here. However, not every heuristic will work for this algorithm. The heuristic must be admissible, which is coming to say that the heuristic must be optimistic in the sense that it gives us an underestimate of the real cost to go to the goal for every node. In our example of Euclidean distance, it is clear that the true cost to go to the goal from each node is always going to be underestimated by the straight line distance to the goal, which is what the Euclidean distance gives us. In the worst case, this algorithm is actually just as bad as Dijkstra, even though for the example we saw here, it arrived much more quickly with fewer steps at the correct path to the goal. For some configurations of obstacles, it might be that Dijkstra is the faster algorithm. And in the worst case, they have the same computational cost. Here, we're just visualizing how these algorithms work differently. We can see that Dijkstra is expanding evenly throughout, whereas A* is directed already towards the goal. Let's compare these strategies. In BFS, we were searching, starting from our start node, at every time trying to choose the shallowest node possible that is a neighbor of the current node. It will return an optimal path as soon as it reaches the goal node, assuming that we have uniform edge weights. A similar algorithm is depth first search, but here instead of choosing the shallowest neighbor first, you try to go deep down all the tree of neighbors first, but on the other hand, the first return path may not be optimal. And then we saw two best first algorithms, Dijkstra and A*, where at every step we were choosing the most promising node to expand next based on some rule. In practice, the computational complexity of our planners that we described here grows with the size of the configuration space. This is because, in the worst case, they need to search every cell of the discretized space. And the discretized space grows exponentially with the number of degrees of freedom of a robot. So for an example, for a manipulator robot, this would be the number of joints. So we would be exponential in the number of joints of the manipulator. Can we do better? What can we do to deal with this complexity? One option is to try to minimize how much discretization we're doing. So our discretization doesn't necessarily need to be uniform. But how feasible this is will depend on the number and geometric complexity of our obstacles. Another idea is to just try to map out the free space. If all we care about is to be far away from the obstacles, this is a valid option. This is actually called a Voronoi diagram, but this might not give us optimal paths in other senses. There's only so much better we can do. General motion planning is in the class of piece-based complete problems, which are some of the hardest problems in computer science. If we want these problems to be efficient and complete, even as our configuration space grows exponentially, we don't currently have solutions to do that. What makes this problem so hard? We see here a few examples that illustrate this point. On the top left, we have the problem of pulling bars apart, called the alpha 1 puzzle. This is hard to discretize. Other problems may have complex obstacles to navigate or many degrees of freedom. This is part of what makes path planning exciting, finding clever ways of overcoming these types of challenges to help robots navigate our ever-changing and complex physical world.